Push a box with a force of 10 newtons. That number alone tells you almost nothing. Push it which way, up, sideways, into the floor. Some physical quantities need a direction to mean anything. Those quantities are vectors and they follow precise rules. Today we define vectors and the two operations they obey. Some physical quantities have only magnitude. Mass is one example. The absolute temperature at a point in space is another. A single number with units fully describes each. We call these scalar quantities. Other quantities have both magnitude and direction. Force has a strength, and it points somewhere. In three-dimensional space, describing such a quantity takes three numbers. We call these vector quantities. Position, displacement, velocity, acceleration, force, and momentum are all vectors. Vectors, together with two operations, vector addition and scalar multiplication, form a vector space. We'll work in the familiar three-dimensional space. Here is the definition. Vector A written with an arrow over the symbol is a quantity with both direction and magnitude. Its magnitude is written with vertical bars or simply as the letter without the arrow. We picture vectors as geometric arrows. The arrow's length represents the magnitude, and the arrow points in the vector's direction. Two operations define how vectors behave. Operation 1, vector addition, combining two vectors into one. Operation 2, scalar multiplication, multiplying a vector by a real number. Vector addition is defined geometrically. Take vectors A and B. Their sum is a new vector. C equals A plus B. First draw the arrow for vector A, then place the tail of B at the tip of A. The arrow running from the tail of A to the tip of B is the sum. This is the head-to-tail method, an equivalent construction. Draw A and B with their tails at the same point. They form two sides of a parallelogram, and the diagonal is the sum. Note what this means. Magnitudes don't simply add. Two forces of equal strength pointing in different directions produce a sum shorter than their combined lengths. Vector addition satisfies four properties. First, commutativity. The order of addition doesn't matter. The sum A plus B equals B plus A. The geometric construction shows why. In the head-to-tail picture, start with A and attach B, or start with B and attach A. Both parts end at the same point, so both give the same sum. In the parallelogram picture, the two orders trace the two sides of the same parallelogram, and both arrive at the same diagonal. Second, associativity. When adding three vectors, it doesn't matter which two you combine first. The sum A plus B, then plus C equals A plus B plus C. Check it with two constructions. In the first, add B and C to get an intermediate vector, then add A to that result. In the second, add A and B first, then add C. Chain all three arrows head to tail, and the final endpoint is identical either way. The grouping changes the intermediate arrows you draw, but never the final vector. Together, commutativity and associativity mean you can add any list of vectors in any order. Third, an identity element. There is a unique zero vector with zero magnitude, such that for every vector A, the sum A plus 0 equals 0 plus A equals A. Adding it changes nothing. Fourth, an inverse element. For every vector A, there is a unique vector, negative A, such that A plus negative A equals the zero vector. Negative A has the same magnitude as A, but points in exactly the opposite direction. Geometrically, walk along A, then walk along negative A, and you return to your starting point. The net displacement is 0. Operation 2. Scalar multiplication. Vectors can be multiplied by real numbers. Let C be a positive real number. Multiplying vector A by C produces a new vector C times A. Its magnitude is C times the magnitude of A. The magnitude of CA equals C times the magnitude of A. When C is positive, the direction is unchanged. CA points the same way as A. Multiply by 2 and the arrow doubles in length along the same line. But multiplying by negative C flips the direction. The vector negative CA points opposite to A, so scalar stretch, shrink, or reverse a vector, never rotate it. Scalar multiplication satisfies four properties of its own. First, an associative law. For real numbers b and c, b times the quantity c times a equals the product b times c times a. The order of multiplying the numbers doesn't matter. Second, a distributive law over vector addition. C times the quantity a plus b equals ca plus cb. Geometrically, scaling the triangle formed by AB and their sum by the factor c scales every side, including the resultant, by c. Third, a distributive law over scalar addition. The quantity b plus c times a equals ba plus ca. Laying ba and ca tip to tail along the same direction gives a total length of b plus c times a. Fourth, the number 1 is the identity. 1 times a equals a. Scalar multiplication gives us a useful construction, the unit vector. Take vector a and divide it by its own magnitude. The result, written as a with a little caret on top and read as a hat, equals a over the magnitude of a. What is its magnitude? It's the magnitude of a divided by the magnitude of a, which is exactly 1. Now notice that dividing by the magnitude is just scalar multiplication by 1 over the magnitude. And since 1 over the magnitude is a positive number, a hat points in the very same direction as a. So a unit vector strips away the magnitude and keeps only the direction. It is pure direction with length 1. Here's the full picture. Scalars carry magnitude only. Vectors carry magnitude and direction. Two operations define them: addition by the head-to-tail or parallelogram rule, which is commutative and associative with a zero identity, and an opposite pointing inverse, and scalar multiplication, which stretches, shrinks, or flips a vector while obeying associative and distributive laws. Divide any vector by its magnitude and you get its unit vector. These rules are the foundation for coordinate systems, which come next. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.